Hello everyone! In this lecture we will look at the Onion router, or Tor in short. I hope that by now you have came to an understanding that encryption alone is not able to provide complete privacy guarantees. Why? Because the fact alone that there is some encrypted communication taking place between two parties may already compromise the privacy. The term metadata is what we use to denote this information about a communication. Maybe you have heard the statement by NSA and CIA that people are being killed based on metadata. For example, if there is information about some person regularly communicating with some terrorist ring, this may be enough to direct a drone strike to the home of that person. The information that is exchanged is not even relevant. So you see that metadata sometimes can be more sensitive than the communication content itself. And this is where the Tor anonymity network comes into the picture, because the aim of Tor is to hide the metadata. So what is Tor? Here is the definition from Wikipedia. Tor is a software for enabling online anonymity and censorship resistance. Tor directs internet traffic through a free worldwide volunteer network consisting of more than 7,000 relays to conceal a user's location or usage from anyone conducting network surveillance or traffic analysis. Let's look at how it works in practice. Let's have a look at this picture. Let's say we have Alice here who wants to establish an anonymous connection over the Tor network to the destination server Jane or Bob here. What Alice does is that she obtains a list of Tor nodes from a directory server. So this directory server here contains a list of IP addresses of users who are running Tor nodes. Alice then randomly picks 3 nodes and establishes a connection through these nodes to Bob. The end result is that from Bob's perspective, it looks like Alice is coming from this Tor node here. So Bob will see the IP address of this Tor node here for Alice's incoming connection. The benefit is that Bob cannot learn the actual IP address of Alice. And another benefit is that if someone is sniffing here at Alice's internet connection, for example her ISP, the actual IP address to which Alice is connecting is not visible. From the ISP's perspective, it appears as if Alice is connecting to this Tor node here. So effectively, there is no single node that would know the entire path of Alice's connection. This node knows Alice's IP address and knows that the packet should be forwarded to this node here. This node here does not know Alice's actual IP address. It sees that this IP address as a source and knows that packet should be forwarded to this node here. This node here knows the final destination but does not know Alice's IP address. It looks like the connection is coming from this node here, and so on. Then later, if Alice wants to connect to Jane, then she uses a different circuit involving different nodes, as you can see here. Note that the number of nodes in the circuit or path here doesn't have to be 3. We can also configure Tor to use just 1 node or use 5 or 6, but you will see that 3 nodes is the most optimal number for performance and security. So the key point here is that no single node knows the entire path. But how is it technically achieved? How can network traffic be sent to this node here and reach the final destination without this node here knowing the address of the final destination? It is achieved through the so-called onion encryption or routing. The message is encrypted in layers using separate keys belonging to each router in the path. So every router can decrypt only the layer encrypted with their key. When they decrypt their layer, they find out the destination where they have to forward the decrypted message. Every router in the path will decrypt layer by layer and forward the data to the next hop in the path. Here's an example. So router A receives the full ciphertext, decrypts its layer, and gets the address of B, where to forward the remaining ciphertext. The router B will decrypt its layer, get the IP address of router C, and forward the remainder to router C. Then router C will decrypt its layer, find the actual destination, and send the original message to the final destination. Perhaps it is better visible in this picture. As you see, on each hop, one layer of encryption is removed until the last node forwards the original message to the actual destination. And you can think of these in terms of TLS connections. First, user establishes TLS connection with the first node, then inside the channel to the second node, and then inside the channel to the third node, and then to the final destination. Okay? All right. Now, these three nodes in the Tor circuit have special names. The first is called an entry guard, the middle node is called middle relay, and the final node is called an exit relay, because this is where the traffic exits the Tor network. Now, why is this node here called the entry guard or the guard node? It turns out that it is very important to pick a good node as an entry guard here and keep it for as long as possible. Why? Because this node here knows the actual IP address of the Tor client. Yes, it does not know the actual destination of the traffic that is sent through it, but this entry guard node is just a step away from figuring it out using a correlation attack. So here is how the traffic correlation attack works. If we try to create a graph with the connections made between each node in the Tor network, then we would see this kind of graph, which doesn't really give us any clue, for example, where this user is connecting, because every destination is possible, right? Now, in a traffic correlation attack, we don't really care about this graph. We can look at the Tor network as an abstract cloud, like this. So here we only see that there are some users connecting to the network and some connections going out from the network. The key idea behind the traffic correlation attack is that if we can sniff this connection here and this connection here, we can verify whether this user here is connecting to this server. This is the so-called end-to-end correlation attack. The data here and here is encrypted, but we can look at the data bandwidth patterns, and if these patterns match, we can conclude that this user is connecting to this server. To create a very strong pattern, we would have to execute an active attack, for instance, introducing some delays here or here and look for the same delays on the opposite end. If we observe the same delays, we can conclude that these two entities are communicating with each other. As you see, in these correlation attacks, there is no need to know the full path inside the Tor network. And this is why it may not improve privacy if we choose more than 3 Tor nodes to build a circuit. The communication will simply become slower because each extra node will introduce additional latency or delay, but the protection against correlation attacks will become no better. So to summarize, if an attacker controls the server here and wishes to de-anonymize the user, the attacker just needs to control the entry guard used for the connection. And this is the reason why the entry guard should not be rotated frequently. In practice, the entry node is picked once and kept for 60 days. If we picked a bad one, we are busted. If we picked a good one, we are secure for the next 60 days. If the entry guard was chosen randomly on every connection, there would be a bigger probability that we would eventually pick a bad one and the attacker will be able to de-anonymize us, right? Right. Now, are these correlation attacks used in practice? From the Snowden leaks, we know a bit about GCHQ attacks on Tor. GCHQ is an intelligence agency in the UK similar to the NSA in the US. This slide shows the idea of how GCHQ could de-anonymize Tor users. The idea is that they would passively collect traffic to the entry guard nodes through the physical SIGINT capabilities they have, for example, by tapping undersea optical cables. Then they would run a malicious exit node which marks the traffic, creates patterns, and hope that the user picks this exit node randomly. If the user picks it, then they know who the user is and where the user connects. End of game. The success of this attack depends on whether GCHQ has the packet timing data of the victim and whether the victim chooses GCHQ's exit node. It is not known whether the attack described here is actually deployed in practice and how successful these attacks are. The truth is that in practice, there are much more trivial methods to de-anonymize criminals that use Tor. For example, consider this case where FBI agents tracked Harvard bomb threats despite Tor. What happened here was that Harvard University received some bomb threats sent over Tor. The university was evacuated and the FBI started an investigation. They found the guy who made the threats very quickly. What do you think? How did they do it? Using some signals intelligence gathering like proposed by GCHQ? Well, it was much simpler. It turned out that the guy was the only one who at that time connected to the Tor network from the campus Wi-Fi network. The FBI agents interrogated him and he simply confessed to the crime. Case solved. Had more students in the campus used Tor at that time, identifying the student would have been much harder. This means that the more users are using Tor, the better is the anonymity level that is provided to the Tor users. For instance, I have installed the Tor service on my computer and it keeps running in the background and communicates with the Tor network whenever my computer is connected to the internet. This way, from the traffic analysis perspective, it looks that there are more Tor users and therefore it is harder to de-anonymize any single Tor user. But anyhow, in the context of these SIGINT attacks, the question is how many of these 7,000 nodes are run by GCHQ and NSA? We don't know, but the good news is that we can always reduce this ratio by increasing the number of nodes in the Tor network by running our own Tor node, right? Now, running an exit node may be tough because our ISP will probably receive a lot of complaints as our IP will show up as the source for a lot of illicit activities. Running an entry guard or middle node should be safe, however. So, if you have a real IP address and free bandwidth, consider running a Tor node. The list of current Tor nodes is public and it has to be public for the Tor to function. You can see the list in this link. If we open it, we can see all the Tor nodes that are currently up and running. Here it shows the country to which the IP address of the node belongs, the name of the node, bandwidth, uptime, the IP address of the node, and here we can see the role of the node. This door icon means that this is an exit node. This folder icon means that it serves as a directory server. And this shield icon means that it is a guard node. So what do you think? How many nodes are run, for example, in Estonia? Well, we can sort by country here, and we can see that there are some nodes run in Estonia, but none of them are brave enough to be exit nodes. There are a bit more nodes running in neighboring Latvia, and there are even 2 exit nodes, as you see here. But the point here is that since this list is public, by observing network traffic, we can see if the user is connecting to the Tor network, and we can also see if a connection coming to our server is made from the Tor network. So if you want, we can block these IP addresses if we don't want the Tor users connecting to our server. Okay? Okay. Now, let's talk a bit about the exit nodes. From the Tor user's perspective, the exit nodes have to be somewhat trusted because there are malicious exit node attacks possible. It is important to realize that the exit node knows the final destination and sees the traffic that is sent to the destination server. If the traffic is not encrypted, for example using TLS, then the exit node can compromise the user's privacy. It means that the exit node can perform passive sniffing, and there is no way we can detect it if an exit node is doing it. There are some claims that this is how the WikiLeaks started. Allegedly, Julian Assange was running some Tor exit nodes and was able to sniff some unencrypted diplomatic email conversations that he published on WikiLeaks. So this is how the first leaks were obtained. Later, when WikiLeaks got publicity, there were also whistleblowers who leaked the information, but the initial source of leaks was plain text traffic from Tor exit nodes. Another problem with exit nodes is that an exit node is not limited only to passive sniffing attacks, as it is in a good position to also execute active man-in-the-middle attacks, modifying the traffic that it carries, right? However, active man-in-the-middle attacks can be detected to some extent, right? So what we can do is that we can check whether the response we get over the Tor network matches the response we get when connecting to the server directly. Such experiments have been done by researchers, and their results were published in the paper Spoiled Onions Exposing Malicious Tor Exit Relays. This here is a table from the paper. This is the list of the malicious exit nodes they discovered. Here you see the IP address, country, the type of attack, and when it was discovered. We can see that most of the nodes run HTTPS man-in-the-middle attacks. Today, hopefully, this would not work because browsers today show very ugly warning messages if a certificate is not issued by a trusted certificate authority. But in 2013, it was more easier to click through the certificate warnings and send data to the attacker. Then we see that there are some hosts that did SSH man-in-the-middle attacks. 2 nodes did the SSL strip attack, removing HTTPS links, rewriting them to HTTP. But this attack should not work today because the most important websites today run only over HTTPS, and browsers enforce HTTPS requests to these websites. HTML injection means that some extra code was added to every return page. And of course, this would work only over HTTP. DNS censorship means that these nodes actually might not be malicious, but since they are hosted in countries where certain DNS requests are blocked, this then, of course, also influenced the Tor traffic. Perhaps you noticed that most of these exit nodes were hosted in Russia. The question then is, are these nodes run by a single party or are these separate attackers? The IP addresses here are different and belong to different internet service providers. However, the researchers found that all of these servers had the same SSH public key, which means that these were actually cloned instances run by the same attacker. Who was behind these attacks? Some Russian intelligence agency or some private sector actors? We don't know. But the point here is that running a Tor exit node provides a powerful man-in-the-middle capability, which has been used by researchers to study Tor usage patterns, as well as by not-so-benign actors to execute attacks against Tor users. All right, let's discuss for a moment the most popular de-anonymization attacks that we have seen in the Tor history. The first mention is the browser fingerprinting attack. The idea behind the browser fingerprinting is that each browser instance and its configuration is quite unique, and therefore websites can extract a fingerprint to uniquely identify the browser. There are many things that can be unique or different. Plugin versions that are installed, fonts installed in the system, screen resolution, even how the video card renders 3D content is unique to each video card and can be measured through browser fingerprinting attacks. This all can contribute to a unique browser fingerprint. So a malicious website can use this to link several seemingly independent requests to a specific browser instance. So even if the requests come from different Tor exit nodes, a website can determine that these requests belong to the same browser. And this can already leak some information about the user's browsing habits. IP address leakage through DNS requests used to be another significant problem. The reason is that Tor can be used only to tunnel TCP traffic, while DNS requests are usually sent over the UDP protocol. Tor has a special method of how to send DNS requests over Tor, but this needs special configuration. If the TCP connection to a server is made over Tor, but the DNS requests are made directly, then the actual IP address of the Tor user can be found from the DNS requests, right? The client-side exploits are a powerful attack vector as well. If the code running on the website can compromise our computer, then this code can make a direct connection bypassing Tor, thereby leaking our actual IP address. This type of attack has been used in practice by the FBI. The FBI took over a website that was hosting illegal content and used a zero-day vulnerability in the Firefox browser to compromise the computers of those Tor users who visited the website. Basically, everyone who visited the FBI's website over Tor were hacked by the FBI, and the exploit code collected the actual IP address of the visitor. We cannot fully eliminate zero-day vulnerabilities in browsers, but what we can do is to limit the attack surface by browsing the web using a locked-down version of the browser. Therefore, today, the recommended way to browse the web using Tor is to use the Tor browser. The Tor browser is a hardened and locked-down version of the Firefox browser with the Tor client built into it. It tries to avoid browser fingerprinting, makes sure that DNS requests are routed over Tor, and also limits the attack surface for client-side exploits. Browser plugins are disabled, even JavaScript is disabled by default. JavaScript has to be enabled for each page separately if needed. In the Tor browser, we can see the circuit that is used to establish a connection to the server. For example, here we see that our entry guard is in Germany, the middle node is in the UK, and the exit node is in France. And hence, the French version of Google is displayed here. Now, another solution to improve security is this type of physical device. This is a Raspberry Pi device with two network interfaces, Wi-Fi and wired. So if you use this device as a Wi-Fi access point, it will make sure that all the traffic is routed over the Tor network and will block direct requests to the internet. So even if someone hacks our computer through a client-side exploit, for example, they cannot make a direct connection to the internet to learn our actual IP address. However, in practice, our computer is likely to contain enough personal information to de-anonymize us anyway, unless, of course, we use a clean machine for that. The attacker can also turn on our webcam and microphone, so these attacks are still possible. But alright, so these are the security aspects that should be considered when accessing services over Tor. Now, another quite impressive feature that Tor provides is the so-called Tor Onion Services, also known as Tor Hidden Services. What it means is that Tor can be used not only to connect to some server anonymously, but also to host services in the Tor network such that no one can learn the actual IP address of the server. And that is quite impressive. Here is how it works. The Tor Onion services are reachable using specific addresses that end with the .onion suffix. Here's an example of how such an address may look. The addresses ending with the onion suffix are reserved for Tor, and they are not actually domain names in the classical sense, meaning that they cannot be resolved to an IP address using the DNS system. To connect to such an address, the Tor service has to be used. As you see, the address does not look very meaningful. These characters are pretty much random. The reason is because every onion service is uniquely identified using its public key. And the onion address here encodes the elliptic curve public key of the onion service. So what it means is that this onion address is self-authenticating, meaning that we can connect and authenticate a service by its address alone because the address specifies its public key. This provides pretty neat security features, as you will see. But okay, how do we actually establish a connection to a Tor Onion service over the Tor network? Here is how. Let's say we have Alice and Bob here. Bob hosts an onion service. The first step that Bob does is that he picks some so-called introduction points and builds circuits to them. So these introduction points are simply 3 random nodes in the Tor network to which Bob establishes a connection. So you see one arrow here, but this connection here is actually established through 2 additional Tor nodes. So these introduction points do not know the actual IP address of Bob. In the next step, Bob advertises his onion service in the database. What Bob does is that he sends to the directory service his public key and list of these introduction points. The directory service accepts this information as authentic because Bob signs it using his private key. So the directory service can make sure that these introduction points indeed belong to someone who holds this onion address. Next, Alice somehow learns that such an onion address exists, and to connect to it, she retrieves from the directory service the list of introduction points. Then she establishes a circuit to a so-called rendezvous point, which is a random node on the Tor network. So there are 2 extra Tor nodes between, such that this rendezvous point does not learn the actual IP address of Alice. Next, Alice connects to one of Bob's introduction points and sends a message to Bob encrypted with Bob's public key. In the encrypted message, Alice specifies some one-time secret and the address of her rendezvous point. Bob decrypts the message and he establishes a connection to Alice's rendezvous point and sends the one-time bad secret to Alice. So this one-time secret is needed for Alice to authenticate Bob. Since this secret was encrypted with Bob's public key, she knows that this is Bob who decrypted it and connected to Alice through this rendezvous point. And that's it. Alice and Bob can now communicate with each other. Bob does not know Alice's IP address, and Alice does not know Bob's IP address. The rendezvous point does not know either, because here and here are 2 extra nodes. The rendezvous point doesn't even know for what onion service it is relaying the traffic. So as you see, in this connection, Alice has authenticated Bob through Bob's onion service's public key, but for Bob, Alice is anonymous, right? Right. So this is how a Tor Onion service works on a high level. Let's see how to set up it in practice. So how can we set up a Tor Onion service on our computer? First, we have to install Tor from the Ubuntu packages. Then, to set up the Onion service running on our computer, we have to modify the Tor.rc Tor configuration file. We have to add these 2 lines. The hidden service dir parameter specifies the configuration directory for our Onion service. And the hidden service port parameter here specifies that all connections to our Onion address port 80 should be redirected to a process that runs on our local computer and listens on port 80. We can specify here also some remote host and port. For example, if we specified here facebook.com port 80, everyone connecting to our Onion service on port 80 would effectively connect through our computer to Facebook. So Facebook would see that connections are coming from our IP address. The first time we start Tor, the Tor service will generate a key pair for our Onion service and store it in this hidden services directory. We can hex dump this private key file and we will see that it contains an elliptic curve key pair. This here is the name of the curve used. To see what onion address corresponds to this key, we can look in the hostname file. So this is our onion address that encodes the public key of this private key. If you don't like this address, we can delete the private key file, restart the Tor process, and we will get a different address. We can repeat it until we get something we like. Of course, only some of the characters here we can get in the form we want, not all of them. The probability to generate a key that maps to some meaningful text here is negligible, but perhaps we can generate a key that will start with some meaningful text. So what is cool about this Tor Onion service is that it is the cheapest way to set up a web server that is accessible to everyone. We don't have to pay for a domain name. Here we can get for free as much onion addresses as we want. The problem, of course, is that the addresses are not very meaningful, and therefore we would have to distribute them in a written form. Usually, if we wanted to set up a website, we would have to host it in some data center on a server that has a real IP address so that others could connect to it. In contrast, this Onion service we can host on any computer that can make an outbound connection to the Tor network. For example, we can run it here in the university on our laptop connected to the eduroam network. So effectively, a Tor Onion service can be used to provide access to services that are behind the firewall. For example, we can configure an Onion service on our computer for SSH port 22. This way, we will be able to connect to our computer over Tor from anywhere. No need for our computer to have a real IP address that is publicly reachable. The Onion service is also portable, meaning that if we connect our computer to a different network, our service will continue being accessible through Tor without the need to update any DNS records. Another benefit for hosting a website using an Onion service is that there is no need to enable TLS for the website, because the connection from the client to the Onion service is end-to-end encrypted by the Tor protocol using the public key of the Onion service. So there is no need for an extra encryption layer, public key infrastructure, and certificate authorities, as the Onion address is self-authenticating. But sure, if we generate another key pair for our Onion service, our Onion address will change, and this then has to be advertised in some authentic manner to the users of our service. So we still need some trust anchor for that. Well, all right. Let's have a look now at an instant messenger called TorChat. TorChat is a simple application that, in a very smart way, uses the security features provided by the Tor Onion Services. The official TorChat client is an application written in Python. To get it running on our computer, first we have to install the Python 3 socks package. In the previous Ubuntu versions, we could install TorChat from the Ubuntu packages, but since the application has not been maintained for several years, the TorChat package has been removed from the Ubuntu packages. The course repository has this TorChat package that you can install using the Debian package tool. When we run it from the command line, we will get a window that looks like this. In TorChat, the communication happens between Tor Onion services. Each TorChat user is identified by a TorChat ID, which actually is the Tor Onion service identifier. The first time we run TorChat, it will set up a Tor Onion service and generate a key pair. This is the TorChat ID of the public key that was generated when I run first the TorChat client. If you want to start chatting with some TorChat user, we have to right-click Add Contact, specify here the TorChat ID of the user, and specify a display name to assign to this user, for example, friend in this case, and specify some introduction message that will be sent to the user. After clicking OK, the connection to this Tor Onion service will be established, and then it is possible to chat with each other as you see here. It is also possible to transfer files over TorChat. The speed is actually pretty good, much faster than sending files over Skype, for example. Now, what you have to realize here is that there is no single party that would know that these two TorChat users are communicating with each other. And this is a super powerful privacy feature which I haven't seen in any other instant messengers. For example, the instant messenger Signal does good work to provide end-to-end encryption, but the Signal server knows who is communicating with whom, and as we discussed, sometimes the fact that two parties are communicating with each other may already be a fatal compromise of the privacy. So TorChat here provides the best privacy guarantees one could possibly achieve. And by the way, here is a link to a master thesis that describes the TorChat protocol and the security of this official TorChat client. Now, the homework task will be to implement your own TorChat client. Therefore, let's look at the TorChat protocol. The good news is that the TorChat protocol is super simple. It does not do any crypto. All the heavy crypto stuff is done by the Tor process running on the user's computer. Here's how it works. Let's say we have two Onion services that want to communicate with each other using the TorChat protocol. As the first step, this TorChat client will establish a TCP connection over the Tor network to this Onion address. After the TCP connection is established, this peer will send a ping message specifying its Onion address and a random cookie here. At this point, this machine knows very well with whom this end-to-end encrypted communication is established. However, this Onion service, for this service, this incoming connection is anonymous. Since we want both TorChat clients to authenticate each other, this peer will extract the Onion address of this peer's ping message and will establish a TCP connection back to this peer. It will send over this connection its ping message specifying its onion address and a random cookie, and will send a pong message sending the cookie that it received from the peer in the ping message. Finally, this peer will send a pong message with the cookie that was received from this peer in the ping message. Now, if you mediate a bit, you will realize that these ping and pong messages authenticate the incoming connections. This peer sent this secret value in a ping message over this authenticated outgoing connection to this peer. Since it received back the same value in a pong message over this anonymous incoming connection, it can conclude that this incoming connection must belong to this peer because only that peer could know that secret value, right? And the same applies to the opposite direction. As you see, there are two connections. An outgoing connection which is used to send data and an incoming connection which is used to receive data. We could as well use a single TCP connection to send and receive data, but for the symmetry and because we need to establish two connections to authenticate each other anyway, the TorChat protocol maintains two TCP connections to each peer. So this handshake process helps to authenticate the incoming connections. For protocol messages, the TorChat protocol uses text commands where the command separator is the new line character. The command message is used to send UTF-8 encoded messages. The status command is used to send status updates, available, away, or extended away. The addme command is used to request an addition to the peer's body list. And profile name to send to the peer's name that should be displayed in the body list. There are more messages, for example, to send an avatar or send files, but these are the most important for basic communication. So the homework task is to implement a TorChat client that is compatible with the official TorChat client. So first we have the official TorChat client running, and our Python client torchat.py we will specify here the identifier of Tor Onion service and here the TorChat identifier of the official TorChat client, which is visible here. The client will establish a TCP connection to the peer's onion address over the Tor network and send a ping message specifying its onion address and a random cookie. Then it will listen for a connection from the official client. Once the official client connects to our client, we should receive from it ping and pong messages. We will verify that the random value in the pong message corresponds to the random value sent in the ping message, and send back the pong message with the value received in the ping message. After this, the handshake is complete. The official TorChat client will send its version information, profile name, and the status. We will send the addme command to get added to the official client's body list. And we will send our status and profile name. As a response, we will receive status update command from the official client. After we write something in the official client, we should receive the message here, and should ask the user to enter the message that should be sent to the official client. So here we entered, "I'm your friend." Then this message is sent and it shows up in the official client. Then from time to time, the official client will send its status to keep the TCP connection alive. So here the message sending is sequential. For each message received from the official client, we ask the user to enter a response. For something more advanced, we would have to use threads, but let's keep it simple, okay? Now, the first thing you have to do is to install the Tor service and set up a Tor Onion service for port 11009 to be redirected to localhost port 8888. This port 11009 is the default TorChat port. The official TorChat client will use this port when establishing a connection to a peer. Now, this port 8888 we choose as a port on which our Python solution will listen for incoming connections. Please use this port as it will be used to test your solution. So your solution should connect to the Pierce Onion address on port 11009 and send the ping command with a random cookie. The cookie must be a random decimal number with 128-bit entropy. Make sure that it has this security level. The cookie must be unpredictable, otherwise impersonation attacks are possible. Then listen on port 8888 for the Pierce connect back. Verify that the TorChat ID in the Pierce ping command is correct. And verify that the cookie in the Pierce ping command matches the cookie you sent in the ping message. Send the pong command with the Pierce cookie over the outgoing connection and make sure that this can happen only after the pong has been verified. Then send the admin status and profile name commands. After every message received, read the user input and send the response message. Again, make sure that this can happen only after the incoming connection has been authenticated. Okay? All right. Now, to implement the listening part, we have to use server sockets in Python. Here is how they work. First, we import the socket library. Then, define a socket, set socket options, bind on port 8888, and listen for connections. Now, this accept method will wait here until someone connects to our port 8888. When someone connects, the accept call will return a tuple. The client socket S, which you can use to send and receive data, and the address, which is a tuple that contains the client's IP address and source port number. So the bind and listen calls will listen for TCP connections on all IP addresses on all network interfaces on our computer. Accept will wait until some client connects and will return a tuple, a client socket that has send and receive methods, and the address tuple with the IP and port. This SO reuse address flag is important because it will force the kernel to reuse the port even if it is in the busy state. This will prevent an error when rebinding, otherwise we would have to wait for a timeout before being able to rebind on the port. If you wish, you can read more about Python sockets here. So that's how to use server sockets in this homework. Here is the list with the most common pitfalls for this homework. Please consult this list in case you encounter some problems. And here are some exam questions. So that is it for this lecture. Good luck with the homework.